Good afternoon, everyone. Paul, thank you for your brief introduction and for your presentation from your work at CITA. It's a great pleasure to be here today. I want to acknowledge the effort and the work from Philipp, Jonas, Oliver, Bastian, and Ulrich, and of course for inviting me to present here some of our work. The work that I'm presenting here today is mainly focused on additive manufacturing of natural materials, namely biopolymers and fibers for the production of building components. This work belongs to the ongoing research of the Tiana campus at our lab, Advanced Ceramic Laboratory at the University of Mino, under my supervision and of Professor Paulo Cruz. Just to give a brief context of our work, I would say since 2016 we start a first set of tests in ceramic materials, starting from small specimens. We moved to building parts, trying to propose new infrastructural roles for those components, but also to explore new aesthetical possibilities. Here we can see a set of prototypes of staves for multifunctional columns, a work developed by another PhD candidate, João Carvalho, and also a beam with a hybrid functionality, with a hybrid system, mixing ceramic blocks with timber elements. More recently, we start to scale up and start to explore 3D printing of concrete-based mortars with the goal, of course, of providing a more sustainable approach on the use of cement in the construction industry, cement and compositions of cement with other natural materials. We are looking for the implementation of something, let's say, similar to what Paul was presenting, computer vision to the control of the flow, but also to build a database for machine learning to control the behavior of the mixes while we are printing. In parallel, we are developing a computational design framework for design and production of custom building blocks for waterfront barriers and piers. Even if the approach could be seasonal, we believe that it can bring big value for those public spaces. And this is something that we are working now. We are starting by doing photogrammetric surveys and custom design our 3D printing elements and blocks for those public spaces. We also have been working, and this a previous work that is being shown here on the exhibition on the BM trade show, and it results from the initial research from Tatiana on the use of biopolymers and natural fibers, trying to integrate it in additive manufacturing process. So it's the work from, say, 3 years ago. And as a proof of concept, we manufactured a wall made of blocks with 3 types of materials or mixtures. The upper part, we are using only cellulose-based mixture with starch. The second row of blocks, we mix the cellulose with sawdust regarding the waste from wood material. And the bottom, we try to mix the cellulose starch with the clay. And despite the lamination of the blocks made only with starch and cellulose, the test shown that the ability of printing, 3D printing with these materials is quite achievable. By adding also a small amount of cellulose to the fibers, to clay, we also noticed that there are less deformation of these pieces when they are drying and fired, if compared to pieces that we were only printing with the clay. So, okay, wrong button. Going back to Biotiles research, it departs from the notion that we need to improve the management of marine resources and to reduce the waste of fishing industry, which is largely made by biopolymer materials. Seafood shells, fish scales, squid skins, and fungal cells are rich in chitin. And chitin is a monomer material, structurally similar to cellulose, that can be obtained from these waste, from the waste of these materials. And ketosane is a polymer that derives from chitin. Considering this, our aim on this specific research was to start testing materials based on biopolymers such as ketosane, starch, and mixing with cellulose fibers. We know that ketosane would introduce some plasticity, the starch would help on the aggregation of the mixtures, and cellulose fibers introduce some resistances. Finally, we are using liquid glycerin to give some flexibility to the composites. Here, just a set of material samples made and tested with the different percentages of raw material. This helped us to, of course, have a visual analysis of their behavior, either the color, either the textures, and helped us to move on and to start to decide which mixture we'll be working on. Here on this last group, we basically were selecting mixture that with more amount of starch and less amount of ketosane, because we achieved a good color, good transparency, and also the fluidity of the mixture that will allow us to print or extrude to the printed extruder. If compared with the behavior of, for instance, of the group 2, with higher amount of ketosane, it gets too hard to start printing and even to pour in a mold as a manufacturing processes. So then we start doing first set of tests. We start for defining grids and trying different mixtures based on ketosane, starch, and glycerin. Basically, the main goal was to start to verify the behavior of the material. We also noticed that, of course, we were printing on those samples. We're printing on a flat surface, and if we move that a fresh printed specimen to a kind of a mold, it will adapt, and after drying process, it will assume that shape. A second set of tests were done. Here we show 2 grids. Here we were printing 4 layers for each one of those specimens, and we were using again different amounts of ketosane and glycerin. And it's possible to understand that the more ketosane, the more rigid and dark the material gets. And also, we see that on the left grid, higher percentage of glycerin has a better plastic behavior. When a force is applied on surface, it changes its shape, but it doesn't. The left doesn't recover it, while the right one, with the lower percentage of glycerin and higher percentage of ketosane, more rigid, it deforms, but gets to the initial shape or recover almost the initial shape. So it's a kind of shape memory effect that you will find on that composition. So we're deciding to mix these two both materials, a more plastic mixture and a more rigid mixture. The one was being used on the base for 3D printing the grid. The grid is the base is a liquid material, doesn't have any celluloses, while the grid had a certain amount of celluloses in order to provide more resistance to the composition of the material. This is just an image of one of the first specimens and tests combining these two. We see that both materials fuse slightly after drying, creating this bioplastic membrane. So in order to now entering on idea of the biotiles, we start thinking on these with challenges of bringing here a prototype to the exhibition, and so we understood that we should try to take advantage and combination of these materials, and try to develop a construction system. So basically, we get this idea of interpretation of the cladding with thin slate panels that we find in many historical buildings, also in Portugal and Guimarães. We have this composition similar to fishing scale superimposition. And so if to achieve the overall shape would be really easy by defining specific molds and pouring the liquid material, then we were using reinforcing the membrane with this structure. We thought also we're crossing here the inspiration of using veins of plant leaves with the aim of acting as a structural reinforcement. The prototype was supposed to have 35 tiles with different shades and textures, and we started producing these. So we made previous testings in July that worked pretty well, and this image is from October when we start doing the final prototype. And you see here the base with liquid mixture, and then printing the base, the fibrous mixture with cellulose above it. And eventually, when all stages are completely successfully, the membrane looks homogeneous and semi-transparent. Actually, I brought a few samples that I'm leaving here. If you guys want to look at it during the break, please do it. And so we have this homogeneous look and with semi-transparency, and the printed areas with the granular finishing.